Hi everyone, this is Hugh from LGST Lab. Today I'm super happy to share with everyone some experimental finding from my recent parabolic flight campaign on the testing of firmly induced phase change propellant management device, also known as a PMD. Let's get right into it. To give a little bit of background as well as motivation to our experiment, we must first talk about space, particularly CubeSat's application in space. With the increasing application of CubeSats in space, there's going to be more and more challenges in terms of propellant management caused by the lack of gravity, which leads to the absence of buoyancy forces. Second of all, CubeSats oftentimes suffers from volumetric constraints, which complicates their designs. And among the many CubeSat propulsion system architectures, cold gas propulsion system is of interest, as oftentimes it is the most widely applied system owing to its relative simplicity, as well as lower cost of operations and constructions. For instance, at our Space System Design Lab at SSDL here at Georgia Tech, we've built many systems using cold gas propulsion systems and launched them to space. However, the application of cold gas propulsion systems comes with their own set of challenges as well. First of all, oftentimes they employ a conformal tank geometry as a result of they're trying to maximize the propellant stored on board of a spacecraft. For instance, if we look at the bottom left here, this photo here is a depiction of a propellant tank for one of our launch previous missions. As we notice, there's going to be a lot of sharp edges as well as corners, other geometric features that cause our liquid propellant tending to wake these areas, causing complications in terms of phase separations. Second of all, in order to maximize our impulse per stalled volume, we oftentimes use two-phase propellants that are self-pressurizing. Essentially, you have a propellant tank that contains liquid propellant only, in which then you implement a secondary propellant tank in which you direct the liquid propellant over, given sufficient time, allow it to essentially vaporize to restore the saturation pressure, and ultimately we'll be releasing the gaseous propellant through a nozzle to generate thrust. This process, however, introduced around a 30% volumetric penalty. Simultaneously, if we were to eliminate this time delay component to our plenum tank, essentially, we need to introduce a inline heater, which would then vaporize the liquid propellant on the way to the plenum tank. This process, however, introduced additional power constraints. So it is obvious that with our current system, there's a need for a more volumetrically efficient as well as a power efficient system that can essentially maximize our efficiency. So the solution that our lab proposed to solve this volumetric and power inefficiency is by using a firmly phase change effect. Essentially, if we were to depict a tank of liquid propellant, say for instance on the left hand side here, we have a bubble located at an undesirable location in which we're hoping to relocate this towards the outlet so that we can extract the gaseous form of the propellant to generate thrust. Our solution and approach here will be introducing a heater at this location next to our outlet, in which then the heater is going to heat and vaporize the surrounding liquid propellant, and increasing the overall tank pressure, which causes condensation of the bubbles at the undesirable locations. Eventually, if given enough time, there's going to be only vaporized propellant surrounding the heaters, and the rest of the tank is going to be liquid form. Here's a ground demonstration of our experiment. As you can see here, this is the undesirable bubble location, and as we switch on a heater, in this case a patch heater, this bubble on the undesirable location is eventually going to reposition over to the desirable case, allowing us to extract it to generate thrust. There's a little bit more details on this paper in which Sam wrote on the bottom right. I encourage everyone to read this. It's super cool. And let's continue. With our experiment being a microgravity application at the end, it is obviously important that we try to launch this in a microgravity experiment and see how our system performs. In this case, our team in our lab is really lucky in that we were selected by NASA Tech Flights to be on board of the Zero G Corporation's parabolic flight, in which we have 4 separate opportunities to test our experiment. Essentially, a parabolic flight is a plane that follows a parabolic trajectory that gives you essentially 15 to 20 seconds of low to microgravity conditions, depending on the flight conditions. The one major benefit of a parabolic plane that provides is such that we, as experimenters, can directly interact with our payload, which would then, first of all, simplify our designs, and as well as allowing for more complex design to be incorporated. Now, let's talk about our experiment VAPOR, which stands for Vaporization for PrOpellant Repositioning. Here's some photo of our experimental test setup being on board on the flight, as well as being on the ground. So in general, the frame itself is going to be supported by 80/20 aluminum extrusions, in which we have power supplies and laptops located on top, which display the performance of our tank system simultaneously. Within the tank sit 5 separate propellant tank systems, 3 of them being sensorized and 2 of them being not sensorized, but acts as controls of heating mechanisms. Each of these individual tanks is recorded by a high-resolution action camera in the front, which allows us to essentially track the evolution of our bubble dynamics. As I've mentioned earlier, we have 5 tanks of different heating mechanisms. So first of all, one of the tanks actually incorporates a patch heater, which makes sense as it is a continuation of our previous ground test in microgravity settings. And the remaining 4 tanks are going to be incorporating a cartridge heater style. Essentially, a cartridge heater refers to a hollowed out aluminum bolt in which we slot in a thermal-resistive cartridge heaters within. So 3 of the cartridge heaters actually incorporates a PMD, in which we'll explain its functionalities momentarily. And we also, for each of the tanks, we incorporate a baffle design within, which allows us to minimize the effects caused by sloshing of the liquid itself, which then minimize the effects it has on the dynamics of our investigation. As mentioned previously, 3 of our cartridge heaters features a capillary PMD design. The reason for this PMD has 2 components. First of all is to increase the vaporization rate efficiency that we have. Second of all is to essentially, once we generate the vaporized propellant, we want a mechanism that we can hold it in place so that we can extract it at a known location to generate thrust. So our PMD design has essentially 2 layers to it. The first component is a essentially capillary sponge, which is comprised of a series of capillary wedges depicted on the bottom here. As this capillary wedge wicks liquid towards the center of the wedge, which is where our cartridge heater is located at, this allows us to vaporize the propellant, in which then, through capillary reasons, we're going to push out this gas bubble into the free stream. But obviously, we're hoping to trap, as mentioned earlier, we're hoping to trap this vaporized propellant for thrust maneuvers. So this comes the second component of our PMD design, in which is a fine layer of capillary mesh that allows us to essentially trap the bubbles. The way that it works is such that as we submerge the capillary mesh within the bulk liquid, these meshes is going to be wetted and essentially generate a surface tension effect that prevents the penetration of these gas bubbles through the gaps. And the bubble pressure that is required of this bubble in order to go through this mesh pressure can be characterized using this equation, which is known as the bubble point pressure. So we've talked about the different components of our experiment. Now let's talk about the overview of our experiment. Here is a canopsis of our experiment. Essentially, you have a taxiing phase in which it is before the low gravity sections. So during this phase, we'll be checking our power, doing some trial runs of the heaters, verifying the cameras and also of our sensors, and checking data storage. And as we were being told by the crew members that we're entering low gravity, that is when we switch on the power supplies to both the heaters and pressure transducers to record our data, and essentially repeat these for 28 times as we have 28 parabolas. During this experiment, which is approximately 15 to 20 seconds, we'll be going to record, first of all, we're going to record the visual data of our tanks, in which we can capture the interface and also the bubble dynamics. Second of all, 3 of the tanks are going to be sensorized, in which we can capture the tank pressure as well as temperature at different locations. With this being a microgravity experiment, it is going to be important that we talk about the microgravity quality that we're able to get. First of all, I'd like to point out that all the y-axes observed here is going to be in the order of g's. So the worst parabola that we've had during the day, during the experiment, is going to be on the average of 0.15 g, in which a decent amount of fluctuation is observed. And during our best parabola, which is parabola 6, we have observed an average of 0.03 G, in which it was ideal. Now, I would like to talk about our experimental results. First of all, it's going to be a depiction of our cartridge heater with PMD. As I would like to point out, prior to the activation of the heater, which is before the LED light, you can actually notice that there's going to be bubbles located at different locations caused by around the capillary wedge, indicating the effectiveness of our PMD. It is also important that we point out that despite the effectiveness of our PMD in terms of capturing bubbles generated from the previous parabolas, there's going to be a detachment of those windows, essentially. This is caused by a material incompatibility issue that we have with the plexiglass that we've used. Turns out it's not really compatible with refrigerants, in which we've not been able to test it previously, but this is going to be addressed going forwards. Now moving on to the patch heater, you can observe that the patch heater actually has a very high rate of vaporization. This is mainly due to the acceleration profile of the plane, in which then the contact area between the patch heater and the bulk of the propellant is going to be between the liquid propellant, in opposed to ground testing, in which we have as propellants being more and more vaporized, the wetted area is being reduced in the ground test. However, that is not observed in the flight test. Lastly, I would like to discuss the results observed by the cartridge heaters. As you can see, this cartridge heater, which is without the PMD installed, has a higher vaporization rate than that of the PMD. This could be further explained if we were to do a side-by-side comparison of all three configurations. First of all, we would like to point out that the patch heater has the highest rate of vaporization. As mentioned earlier, this is mainly due to the acceleration profile of the plane, in which then the vaporization rate is followed by that with just cartridge heaters, and lastly, the cartridge heater with PMD. This actually indicates the presence of an additional thermal mass or thermal inertia added by our PMD, which delays the onset and cessation of bubble generations of the system. Overall, to conclude our experimental finding, it is important that we point out, first of all, we've been able to prove that both cartridge heaters and patch heaters were effective in terms of vaporizing our propellant. And then it is also pointed out from our experimental results that PMDs are necessary, and in this case, as shown in the case with the PMD installed on the cartridge heaters, was effective in terms of retaining all the bubbles that are being generated in previous parabolas. However, it is important that we acknowledge that there's going to be impacts caused by the installation of PMDs. The first being the increased thermal inertia introduced by the PMD structure. This leads to a delayed onset and cessation of bubble generation of our system. And lastly, there's a observed reduced rate of vaporization when we have the PMD installed to our cartridge heater. This actually indicates a lot of potential future works we can do going forward. First of all, there's going to be some refinement on terms of our PMD design, particularly the material incompatibility issue that we've encountered. And also we're looking into characterizing our thrust, as well as improving or developing a vaporized propellant extraction mechanism. But that is the end of our presentation. Here's some related publications that we have regarding the topic. I encourage everyone to read them, and thank you very much for your time.